All right. Hopefully everybody's back from doing their bio business. This is going to be weird because I've never actually presented with a laptop with my speaker notes that far away. All right.
That's good.
That's it.
Okay.
We can't kill these?
No, unfortunately. Well, you turn those off.
You turn them all off and everyone will go back to sleep.
Yeah. The other one.
Camera can't see.
The camera can't pick it up.
No, that's all on.
All right, now I'm just having a seizure.
No, I'm just going to flick back and forth. I'll keep walking around the room turning lights off.
All right. So reverse engineering is going to be what I'm talking about today. It's a 101 talk in that it's going to be the very basics of RE. I'm not going to get into advanced unpacking, advanced binary analysis. It's just going to be very straightforward reverse engineering. Specifically, the easy way to talk about reverse engineering is within software cracking. The same stuff that you guys do or may do. Piracy, that type of stuff. So what I have is I've passed around CDs to many people. They're Windows binaries that are very basic register me type applications that we're going to walk through a couple of those towards the end of this when we get to the demo part. And essentially we're going to go through the basics of cracking, and we'll show you guys how to crack 2 or 3 of those 5. Leave the last couple ones which get progressively harder for you guys to figure out, and then email me if you have questions, that type of thing. There we go. All right, agenda. Introduction, it'll be about me. I'll keep it brief because I'm pretty boring. X86 System Basic. So what we're going to be talking about is X86 architecture. We're not going to be talking about Spark architecture or any of the multitude of disparate systems. We're going to be talking about just standard X86. We'll go over some of the basic opcodes. It's just a slide or two. Go over a little bit about the PE, the Portable Executable File Format, which is the Windows executable file format. Then we'll talk about some of the common tools and some of the other things, the other ways to reverse engineer applications. Finally, we'll get into the demos of the actual crack-me's. Go quick review and questions. All right, introduction. Pretty boring stuff. I belong to a couple different hacking groups that I've been affiliated with in the past. I currently work as a information security consultant for a local company. And actually we'll be moving to Charlotte to join a new company here in a few weeks. Primarily focused on application penetration testing. In other words, I break stuff. I like to break stuff. My main focus is actually web applications, which I talked about last year. I've only been studying reverse engineering probably for about a year now, so I'm not an expert in the field by any means, but hopefully I'll know enough to get through this slide deck. Presented at major industry conferences, presented at Hope, presented at a bunch of different conferences, taught courses, etc., etc. All right, X86 System Basic. So what are the major components of an X86 system? All these laptops that you guys have on your laps, they all break into 4 major areas. It's going to be the processor, the main memory, I/O modules, and system bus. These 4 areas are going to be paramount to reverse engineering. We're going to predominantly be working in the processor area, which essentially controls the operations of the computer and executes the data processing functions. So every time you load a binary into memory, it takes all those hex values, those bits and bytes, puts them into memory, and the processor brings those into the processor and executes them in a fetch and execute cycle, which I'll get to in a little bit. The main memory is where everything is stored when you load up the binary. It gets put into the main memory. It's typically volatile. It holds data as well as the program code. And I will talk a little bit about the segments that it can be broken into on a later slide. I/O modules, essentially that's stuff like your printers, your disks, non-volatile storage, those types of things. It's essentially where data can be stored in longer term than the volatile memory. It's typically significantly slower than your volatile memory space, but obviously there's benefits that it can be stored longer term. And then the system bus, which is the communication path between all these components. This is a very high-level overview. They have long, drawn-out operating system courses that go into the detail of paging of memory and all those types of things. But this is the general high-level architecture of all those systems you guys are used to working on. By the way, if there's any questions, just throw the hands up and ask. If I don't know it, I can hopefully refer you to a page or a book or something that might be able to help you out. All right, so within the processor, we have the concept of processor registers. What a register essentially is a very small, usually 32-bit, hunk of very fast memory. It's built into the processor. It's faster and smaller than main memory. There's user visible registers, are which registers that the application can control and modify, can put data into, can put operations into, can put pointers into. And then there's control and status registers, which typically aren't usable by the application itself, but are the results of, say, when you do a arithmetic operation and there's an overflow within that operation, it'll set a flag within the control and status registers. So those are we're going to be playing a lot with the registers when we do the crack-me's, but the main thing to remember is they're just 32 bits of memory, of blank space that can be modified per the application's requirements. All right, so within the X86 system, we have 8 general-purpose registers, GPRs, EAX, CX, DX, DX, ESP, SI, and EDI. These general-purpose registers all have a primary focus of what they're intended to do, but applications can definitely use those in different ways. Essentially, the EAX is an accumulator, which tends to hold arithmetic operations and results of your additions, your subtractions, your multiplications. The counter register is primarily used for looping. When you have like a for loop or something in your code, it's probably going to set it in the ECX register. Data register, EDX, that's pretty obvious what that's for, just for storing data that may be inputted into the application. Your base register is a pointer to the data section of the application. Your stack pointer is a pointer to your stack within the application, and I'll go through these a little bit more detail when we bring up the debugger so you can see what those things are used for. Source register and destination register, again, are for stream-based operations. You don't really need to know what they're used for. You just need to kind of know when you bring something into the application, you watch that register change with your new data, that's where the data is going. So registers, again, are just very fast, volatile hunks of memory. General purpose registers, 32-bit wide. They're called extended registers, EXX, as we just saw. There's a couple different ways that you can address the registers. You can address the register as, for example, EAX. It addresses the full 32 bits. You can address it as AX, CX, DX, which is going to be your 16 least significant bits of your 32-bit register. So if you have a 32-bit register, the least significant bits are going to be the furthest on the right. And the application will reference those with these smaller, different mnemonics, so to speak. And you'll see those when we look at the disassembly of our application. You'll actually see these called out. You'll see the extended registers called out. And then you'll see things like AH, AL, CH, CL, which are the high and low order bits of that 16 bits of the 32 bits. So you can reference just 8 bits of the register by using an AH, AL, or CH, CL designation. This will make more sense when we actually go through the demos. Everybody glassy-eyed appropriately at this point? Any questions at this point? Okay, so there's also 6 segment registers. Now we're still talking about within the processor. There's 6 different segment registers that are used by the memory module to point to segments of loaded code and thread-specific data. So when you fire up your binary, these different segment registers are going to point to the segments that are specific to your binary that you're loading up. A typical binary is broken into different segments, such as a data segment, a resources segment, a text segment, and these are going to point to those different segments of your binary program. Your stack segment, code segment, data segment, etc. Not used all that often, but within the debugger that we're going to run, you're going to see where it references the stack segment with an address plus 4 bytes. You'll see stuff like that, and that's referencing these basic pointers. All right, so other registers. Flags register, which is what I talked about in the beginning, one of the status registers, is used to denote results of operations in the state. Holy crap! Everybody's awake now. Boring shit just went out the window. Flag registers, status. They hold status for operations, errors, error codes, stuff like that. And the EIP, which is going to be a very important register for us, is the instruction pointer. It's the next instruction that's going to be executed. when running and debugging the application. So the stack. I think originally there was supposed to be a talk about buffer overflows, but I think it may have been canceled and replaced by something else. So I'll actually address some buffer overflow issues as I'm going through this as well. So I don't have a slide deck specifically prepared for buffer overflows, but I can give you the general idea of how they're going to work while we're in the debugger. So a stack is essentially a place where temporary data is stored when the application is being run. So when your program makes a function call to another function, all those arguments that are passed, all of the previous state of the processor has to be saved somewhere before you can get into the new function. That's what the stack is used for. All that stuff is pushed onto the stack, your new code is executed, and then the original state of the processor is popped from the stack, and you can return to your original entry point. So essentially it's a section of memory that grows downward to lower addresses in x86. Don't get confused if you go look at Spark or something else, because it's going to grow upward. It's an area intended for storing temporary values, and it's the area we abuse when we're conducting stack overflow attacks. So I'll talk about that a little bit. I missed the most important point. It's a last in, first out data structure. So the last item that you put in is the first item that you take out. So think of it as a stack of books. If you take a stack of books and you put an item onto the stack, you put another book onto the stack and another book onto the stack, the only one that you can get out is the top one. Okay, that's a stack. All right, so some final x86 System Basics miscellaneous notes. x86 is Little Indian, which is backwards. Indian, however you pronounce it. I can never pronounce that word. So your typical 32-bit word, like if we were to use these hex values, B0, B1, B2, B3, is represented as B3, B2, B1, B0. It's flipped backwards. And what will happen is you'll run into points where you're trying to search for a string when you're cracking something or reversing something. And you have to recognize that, okay, my ASCII values for that string are going to be in reverse in the application. Now, most of your debuggers and most of your disassemblers, when you say search for a string, will automatically reverse it before it does the search, so you can just type your string in. But don't get confused if you're looking through the hex data and you see it backwards. And last but not least, addressing modes. Addressing modes can get rather confusing because there's a number of different addressing modes. So if you're trying to look at, for example, hunks of memory or registers, there's different ways you can address that. Okay, there's register addressing, which is specifically move data in AX to data in BX. Very straightforward, move between the two registers. There's immediate addressing, which would be move this hex value, 0x0 or 040 in hex, move that into AX. That's pretty straightforward too. There's direct memory addressing, which you'll see when we get into the debugger, which will be, for example, move what's at address 102 hex into AX. And there is a number of other ways, indirect addressings, indirect register addressing, which I'm going to save for if we ever do a 201 type talk on this, because those get a little bit trickier. So the first couple crack me's that I gave you guys are going to use basic register addressing, simple pointers, and some basic memory addressing. So those should be all, hopefully, we'll have to get into. Okay, opcode. So at the beginning of the talk, I talked a little bit about how when you load a binary into memory, that string of instructions are put into memory. Those string of instructions are made up of opcodes. Those instructions are fetched and executed within the processor. There's a lot more to it involving interrupts and a bunch of other stuff that I'm going to, again, put to the side. But the basic gist of it is instructions are stored in memory, brought into the processor, and executed. Those instructions, if you break them down, are made up of opcodes and a certain number of operands. Okay? So if you look at an instruction, it's going to be, let's say, 32 bits wide. The first 8 bits might be the actual opcode, the operation that the processor is going to execute. The remaining 24 bits are the operands. So, for example, you'll have an add opcode, then you'll have an operand that says register AX, and an operand that says register CX. That will add CX to AX and put it in AX. Okay? So an instruction is not just add. It's actually, one instruction is going to contain the operation to be done and any appropriate components that it needs to be done on. Your disassembler debugger will decode that just ugly-looking hex into something that's quasi-human readable. Basically, it's human readable if you know assembly. which hopefully by the end of this you guys will have a basic understanding of looking at assembly and understanding what it's going to do. Common opcodes. Here are some of the more common opcodes that we're going to see. Anybody know what any of these do? I mean, what they try to do when they write assembly, they try to look at the assembly and make it something that, hey, okay, a loop, hey, it's probably going to be a loop, right? A MOV, it's probably going to move data from one location to another location. So these mnemonics are usually pretty easy to figure out. There's tons more than this. And we're not even talking about MMX extensions. We're not even talking about extensions beyond the basic X86 opcodes. So there's way too many to remember. Get yourself an Intel manual.
Where do you get those?
Intel manuals are, do you know how often those come up for order? Because you ordered them. You showed me that link, right? Do you know how often they come up for order? Didn't you show me the link for ordering those?
Yeah, you get them all the time.
I think they back order.
Is it on their website?
Intel's site, they offer 4 manuals, and they end up getting back ordered because they only offer so many of them per quarter.
Really?
Yeah. So they only offer so many of them per quarter, but they're free, including shipping. So if you can go to Intel's site, $5?
I think there's
Five manuals? Okay.
Yeah.
There's 4 or 5 manuals, and they're free, including shipping. Go to Intel's site, search for it, find me online, I'll send you the link. I don't know it off the top of my head. But get the Intel manuals. Worst case scenario, Google for opcodes, and bookmark yourself a half a dozen good pages that go over the definition of what the opcode you're interested in. There's just way too many to try to remember. Even people I know that do reverse engineering and malware analysis full time, they keep these references with them all the time.
Intel, I would just put them out there as PDFs. It's not like it's,
Right, they should, but they don't. So yeah, I got a copy because Skell pointed me to the site. I have been using just basic Googling for all of my RE work, but I got a copy of the books in my trunk, actually. Okay, so one other thing I want to go over before we actually get into doing some of the reverse engineering is we'll talk about the PE file format. This is Windows specific. Back in the day, Windows used the MS-DOS file format. Now they use a thing called the PE file format, and I believe that was with WinNT3.1 that they switched over their file format. Essentially, that .exe file that you have, or object code or DLL that you have, it's used in the Windows operating system. It contains different regions. Okay, those different regions are broken out. Typically, what you'll see is a .txt region, a .data region, a .rscs region, which are your text, your data, and your resource regions within that binary file. When the binary file is executed, each of those regions is loaded into a section of memory, and that section of memory is tagged for specific permissions. For example, your TXT might contain all of your actual operations, the instructions that are going to be executed. When that's loaded into memory, that memory section is going to be tagged for reading and executing. Then you might have a data section which might be tagged for reading and writing, but no executing. So each of those permissions are mapped into each region so that only certain areas can be executed and only certain areas can be read or written. And finally, one other thing that's kind of a more advanced piece of information that I wanted to make sure I got out there for the PE file format is within the PE file, there is a table called the import address table. The import address table holds addresses for any kind of reference that might be made to a separate DLL or a separate Windows API call. That is dynamically, I believe it's dynamically loaded by the linker when you load it into memory. So essentially that's a table that's going to have all the references to where to look for the different pieces of external APIs and external DLLs. The reason why I want to bring it up is some more of the advanced binaries are going to use things called packing, which are going to encrypt the binary or otherwise obfuscate the binary. When it does that, it tends to destroy and blow away the import address table. So when you unpack the binaries, you have to rebuild the address table. Now, this is, again, more of the advanced type stuff, but the general idea is that there's a table in there that references locations for other DLLs and for other components. Okay, so the PE file format. Yep.
What's in the resource region?
That typically holds static strings, like if you compile a binary with static strings, that'll end up in the resources section. What we'll do is when we fire up these binaries, we'll try to look through each of the resources and we'll see what's in each one. But yeah, in general, you can have like static strings, static tables, things that might be statically compiled into the binary. Those will end up in the resources section. Data is used again predominantly for inputted data, memory space that's used for interactive. That's not like a hard and fast rule, because that could change based on how the program is coded, but that's the general concept. Any other questions so far? Hopefully I'm not killing people too bad. All right. So when you compile a PE file, it's compiled to a preferred base address. And what that means is, and this is different between different file structure types. Like Linux, ELF does not compile to a preferred base address. It actually compiles with dynamic addressing, I believe. But essentially, the preferred base address is the address in memory where that binary wants to load. Because then all the addresses that are absolute within that binary are going to be properly based, right? So if it loads to hex value A, and the application within it says, within the application code says A plus 10 somewhere, it's going to, says B as an absolute value. It's going to know where those are. Now, if it tries to load that binary and that space is already taken, the preferred base address is already taken, the actual operating system has to rebase the application, which creates a new base address wherever it's going to load it into. And then it looks at every absolute value within that PE file and changes those to be appropriate to the new base address. That's not the best solution, and that's why I kind of like ELF format a little bit better, using more of the relative addressing schemes. But essentially, the operating system will rebase it, and it's going to slow the program down a bit, pretty significantly, actually. So as you can see, I'm just glossing over PE file formats. This slide describes the PE file format in detail. It's on the CDs I was passing around. There's a lot to it. I mean, people really, you can really spend a lot of time digging into the PE file format. And ELF too. ELF, you can do the same thing. I don't know 1/100th of what is on this slide, but I gave you the basic general idea of what PE file format is. This URL down here, openrce.org, I highly recommend to anybody who wants to do any kind of reverse engineering work or learn anything about reverse engineering. It's a really cool site, and a lot of really, really smart people frequent those forums, so I highly recommend that site. Okay, so far what we've talked about is specifically static binary analysis or runtime binary analysis, essentially debugging. I've given you the basics of what you need to know to debug and look at an application. Reverse engineering is a lot more than that. If I give you a piece of code, you're not going to want to drop it straight into the debugger and run it and see what happens. If you do, you better do it in a sandbox. Now, the stuff I've given you guys out there, that's exactly what I want you to do to it, because I'm hoping you trust me enough that I'm not going to try to, bomb your machine. But there's a lot more to reverse engineering than just dropping it into a debugger or a disassembler. This is a list of tools that reverse engineers use every day. We talked a little bit about debuggers. Those are for interactive analysis of the application while it's running. And I'm going to go over in detail one up there that's free called Ollie Debug, which is on the CD I've been passing around. Disassemblers, which is typically used more in a static or dead listing type analysis of the binary, which decompiles the binary and breaks it out into the mnemonics that you can use. It's used to analyze the application when it's in a static state as opposed to a runtime state. The best one on the market is Interactive Disassembler Pro or IDA Pro. Great tool, way too expensive, but really cool tool. Emulators, again, we talked a little bit about those. VMware and Virtual PC. If you get your hands on malware, or if you get your hands on something you have no idea what it does, run it in a sandbox that's isolated. VMware and Virtual PC is not 100%. I've heard of rumors of ways that code can break out of those environments, but it's not easy, and most of your binaries aren't going to do that. So if you're extremely paranoid about it, get a separate machine set up, get it isolated, and do your testing there.
You can break out of VMware?
I've heard rumors you could. I personally have not been able to see it done. So process watchers and tracers, these things come in really handy. Sysinternals is the best site for process watchers and process tracers. You can view things such as all the TCP connections coming up, file accesses, DLLs being loaded, just tons of stuff about the binary that you've probably never even really had a clue was happening on the underlying pieces of your system. Even if you're not getting into reverse engineering, go to sysinternals, pull these files and dork with them. They're free, and they're really, really useful for debugging application operating systems. Let's see if anything I want to talk about specifically on those. Nah, guess not.
Are you going to have this PowerPoint available online?
Yeah, I'll make it online. I'll either put it online or give it to the organizers here to make available. So yeah, that's not even all the tools, right? There's even more than that. So package sniffers, which I guarantee you've all used at some point in time, those are very useful if you're trying to reverse engineer protocols that may be going across the wire. Ethereal, TCP dump, the same stuff you guys are used to using. Unpackers, which I talked a little bit about, some of your more advanced binaries and a lot of your malware are going to use packers. Essentially, those unpackers are used to automatically unpack the binary, unencrypt the binary, and rebuild the import address table so that you can then drop it into your disassembler debugger and be able to view it. Some packing algorithms are so advanced and so new, you have to actually manually unpack them, and that's a pain in the ass. The essential concept with packing and encrypting is that when you drop it into a debugger or a disassembly tool, it's going to look like encrypted garbage or obfuscated garbage that you're just not going to be able to figure out what the heck it is. Now, at some point, that binary has to become unencrypted and turn into non-garbage before it can run on the computer. So essentially, what you have to do is progress through all of that decryption routine, trace through all of that, find what's called the original entry point, at which point the application looks clear again, and then begin your debugging. So it's a pain right in the butt to do manually. So there's a lot of good unpackers out there, and if you come across a program that's just not looking right, it just looks odd, download some unpacking detection tools, run it through those, and maybe, hopefully, it'll be a commonly used packing routine. There's also automated import reconstructors to reconstruct the import address table, like we talked about. And fuzzers. Fuzzers are used for fault injection. I talked last year about doing web attacks and using fuzzers for attacking individual parameters of a website. Exact same concept with an application, except you're going to be fuzzing things such as memory space, protocols, basically things that are more application and code specific, files that may be read into memory, that type of stuff. And there's a number of good fuzzers and fuzzer frameworks that are out there. They're kind of difficult to use because they require a reasonable understanding of coding because they're just frameworks and you typically have to code something around them to get them working. All right, enough of this crap. Do something fun. All right, so anybody who's got the CDs or has the data, go ahead and fire up, hopefully copy it to your drive so that it can save its temporary files and stuff instead of running it off the CD, but go ahead and fire up Ollie Debug. And hopefully you're going to get something like this that's blank. It's not going to have the code in it. But hopefully you're going to get something like this. Crap, I'm not going to be able to do this. You get something like this up on your screen. Is there any way that we can get that up here, the laptop up here? Or is that not possible, Nick?
It's connected to the...
Is the cord long enough to get a laptop up here to actually use it? All right, well, I'm going to have to sit with my back to everybody then. So you're going to come up with a screen that looks like this. Anybody not get this screen?
With nothing in it.
Right. There should be no code in it because we haven't actually loaded an executable. All right. Oh, yeah. That's the end of my slide deck. Yeah, that's my son. Everybody go, ooh, ah, cute.
Ooh, ah, cute.
Thank you. Well done. All right.
Looks just like Lex.
Hey, now. All right, so this, you should see something similar to this. If you go ahead and do a file open and open up exe1, that's the first one we're going to run through. Oh, it's kind of off the screen. That sucks. All right, so let's talk about the different regions that we have here. In the upper left corner, you see the disassembly of exe1.exe. That's this section right here. Over here, if you look at the top of this right here, you'll see the actual registers that we talked about at the beginning of the talk that holds the temporary values that are going to be used.
There's a laser pointer.
Oh, is there? Sweet.
Which one?
Nick, do you know how to use a laser pointer on this thing?
The button at the top should be work. You might not
Nope.
be able to see it. There you go.
All right. Anyways, I'll just continue to use my little funky finger shadows. So we talked a little bit too about right here. You'll see the actual sections of the application that we talked about. Down here, you'll see the memory that's loaded and the hex dump of what's in memory. And let me actually move this over. This will be your stack in the lower right corner. All right. So let's just go ahead and do debug run and actually run the application. So what this application is we don't know. It's been sent to us. Whatever. We want to crack it, or some program, some application we downloaded. We want to crack it. So it loads up and it's prompting us to enter a code to register. And nothing happens. I mean, it just doesn't work. It's not registering for us. So you can get some more information about it there, and then you exit. So first things first, let's actually go ahead and restart it. All right. So has anybody taken the time to go through this at all yet? Or am I going to be flying without any help from the audience? Option B. All right. So when you fired up the application, we want to look at it again. Let's look at it a little bit more closely. We have a button that says check, a button that says about, a button that says exit. We have a text box that we're going to have to get data from, right? The application is going to have to pull that data into memory somehow. And then we have a string down here that says unregistered version. So now let's actually look at the code. Run. Restart. All right. So Ollie Debug does some really cool stuff in that over here it actually breaks out chunks of mnemonics together and gives you the general idea of what that chunk of mnemonics is going to do. So we see here, okay, exit process, get command line A, get module handle A. This looks like it might be the setup and shutdown routines of the application. Load icon, load cursor, create a window. I mean, this stuff is pretty straightforward what this stuff is going to be doing without even actually looking at all at the actual opcodes. Let's see. Get message A, translate message, dispatch message, create window. Okay. Create some more windows. And look, some of the text here. Unregistered version. About button. Check button. Exit button, right? So there are your buttons. It's creating the application at that stage. Okay? It's actually creating the program. I'm sorry, the actual windows that you're going to be viewing. Okay, unregistered version. Get window text length A. Does anybody have any idea what that might be for? Is this thing on?
What does it say? Window test length?
Get window text length A.
So it tells you how many characters it is?
Bingo. So what it's doing there is it's checking the character length of what you're putting into that text field. That could be interesting. Why would it check? Why would it care the number of characters? Well, it's probably doing something like that when you're doing your registration code. Well, we'll come back to that. Get window text A. That's the code where it's getting the text out of that window.
What's the window?
Out of the window that was built, that text bar. What the heck is that? Some funky ASCII string. Who knows what the heck that's for? All right, we succeeded with cracking success. Or, there's a failure one down here somewhere. So about, there's your about, what happens when you click the about button. So we haven't even looked at the opcodes yet. We have a general idea what this code does. Now, granted, this thing is tiny. You'd have to do a lot more searching in your typical cracking of an application. But for concept's sake, let's go ahead and look at this a little further. So does anybody have any idea where we should try to break this application when we're executing it? What we're going to do is we're going to drop a breakpoint on there. Can I get a time check? I don't even know how long I've been going.
11.
Okay, so it's been about 30 minutes. Cool.
Yes.
So what do I got? 30 more?
30 minutes.
Cool. So what we're going to do is we're actually going to run the application and we're going to stick a breakpoint in there using the debugger to stop the application so that we can analyze the memory and go line by line with the opcodes and see what is being done to the data that we're passing in. Anybody have any idea where they want to break it? Where they want to put a breakpoint?
right after the button that says get?
Get window text.
Yeah. Right before you
Get window text or get window text length. Okay, because there might be a problem with that. Most people will drop it right on the get window text, which is a great idea. However, this particular piece of code is actually checking the length first and then not actually bringing it in. So if you drop a debugger on your get window text A and you don't have the right number of characters, it's never going to break. And that's going to kind of drive you batty. That's one of the catches on this first one. So let's drop it on the get window text F2 for anybody who's trying to follow along. You go onto the line you want to break on, you hit F2, and we're already running, I believe. No, we're not. Let's go ahead and run it. Okay, now let's enter a string. Let's check. Okay, so we broke. All right. We broke on the line that seems like it's going to pull the data, that's going to check the length of the data that we entered. So what we'll do is we'll go ahead and press F8, which I believe is the right button. Right, step over. There's a step into and step over. You're going to get used to using those a lot. Step into steps into a call. So sometimes there'll be a code that says call this other section of code. If you do a step over, it'll call it all and then come back. If you do a step into, it'll stop at the first line of that called code. So we're on a call here that's calling get window text length A. It's calling some other chunk of code. We're just going to go ahead and say call it. Now, I don't remember how many characters I put in there. Does anybody know what string I put in there? It doesn't matter because I can tell you by looking at this. But if you look in the upper right corner, you'll see EAX6. My vision sucks. Yeah, so I put in 5. I put in 5 characters. And you'll see what happened with that call is the window text length, or the number of characters that I put into that text window, is now that value is sitting in EAX6. Okay? And what you see here on the line that's highlighted is compare EAX to hex value 0B. Anybody know what hex value 0B is? 11? All right. So it's saying compare the number of characters that we put in to 11. Okay? JNZ, if you look in your opcode little sheet that I gave you, is jump if not equal. Okay, so if it's not equal, if that previous compare was not equal, we're going to jump to this other section of code. Now, you can probably guess that that section of code is something that's going to say unregistered or broken, and you could try to trace through that if you wanted to. And we'll go ahead and just, look at that section of code. And it actually, what that section of code does is exactly what we thought. It pops up the window, and we'll just go ahead and run it out. And nothing happens. It just breaks. Didn't work. All right, so now we know it's 11 characters. 11 characters. We run it again. And we're back to the same place we were before. We compare 0B, which is 11, which is the length of our string that we entered, with 0B, jump if not equal, so we're not going to jump. We're going to continue through. So here's the section of code where it's actually going to get the window text. So we've passed the first check. The first check was check the length of the string that we're entering, see if it's 11 characters. We passed it. And get window text. All right, so there's something I want to point out on this line. So we just did the call for get window text A. So we brought that into memory somewhere, okay? If you look at the line we're on now, that looks really weird. We were talking a little bit about indirect addressing and using pointers. This is using pointers. So if you read this, it says compare a byte in the data section, this funky hex address, to the value 2D. All right, so if we look down here, this is our memory section. Let's look at that funky hex address, 40234B. 40234B. Look at that. What's in memory right there? ASDFDHJKLPO. That's exactly the string I entered. So now you can see where the data that we entered is sitting in memory. And what this actual operation is trying to do is compares the first byte that's being pointed to by this address with the value 2D. So the hex value 2D in ASCII So I've also included this table on your CD. 2D, 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 2D is a dash. All right. So it's comparing 4023-4B, which is actually which character, right? 48, 49, 4A, 4B. So it's comparing the fourth character against a dash. Okay, so we just figured out that the fourth character's got to be a dash, which, needless to say, if we go ahead and continue, we just jumped way past the cracking success area. We failed that compare. It didn't work. All right, so let's pull it up again. Change the fourth character to a dash. Check it again. We'll get back down to that compare. Go ahead. Jump if not equal. We passed it. We're still in the routine that's checking the string. Okay. Now it's moving. Okay. The byte pointed to within data section, that address, it's moving 4-1 into that address. 4-1, if you look it up in your ASCII table, is the capital letter A. So it's moving an A into the fourth character slot. And if you look down the lower left corner where I have the pointer, when we go ahead and execute the move, my data changed to a capital A. Okay, is everybody following this, or am I kind of, because I'm zooming through it? Okay. And now it looks like it's going to do another compare of a data spot in memory to the dash again. It's going to look at 4234F. So we have 48, 49, 4A, 4B, 4C, 4D, 4E, 4F. Okay, so now it's comparing that to a dash, probably because it wants a dash in there. We hit F8 on that. Oh, we jumped right past. All right, we didn't have a dash. So we go, let it run out, go back here. I think it's that one, right?
Yeah.
Okay. And we check it again. We jump through, we get our window text. Move in the A. If you look in the lower left, you see it dropped an A in. Here's our compare. Here's our jump. Okay, and if we look in the lower left, it's going to move a big capital B where the original dash was. So now we've passed the first two checks. We know that the fourth, I think it was the eighth character, are both dashes. Now what's it doing? Well, let's look right here. If you look where that funky string I called out before, and right above it, it's actually our string that we've been modifying as well. Okay, so what's it trying to do there? I'm not quite sure yet, so let's go ahead and step through. All right, so the next line is it moves the value 0A, which is hex for 10, into ECX. We don't know what for yet, but if we do that and you look in the upper right corner at the red, you'll see the value 10 was dropped into ECX. Okay, now it's going to increment the byte pointer at data section ECX plus 40234B. Oh, that's funky, or 348. So it's incrementing it by 10. All right, so 2, 3, 4, 5, 6, 7, 8, 9, 10. Well, let's just go ahead and F8 through it and see what it does. It's counting something down. So you see in the ECX is counting down? It's looping something there. But it's not, and if you look, wait a minute, look at our string changing. See it changing? Let's run it through again. Check it one more time and let's see what it does. All right, so it's incrementing the byte at that address by 1. Anybody figure out what this is doing yet? Watch the string. Watch our string in memory. You can either watch it down here or you can watch it right there. Okay, watch it in memory. See them all changing as it loops through? It's incrementing the ASCII value by 1 for each of the characters within our string. And then, I mean, you could probably guess it through at this point what your appropriate string is supposed to be. Okay, so then it loads the two values into ESI and EDI Up in the upper right corner, you'll see the ESI and EDI registers, and you'll see the funky string that we started with that nobody knows what it's for yet. And then you see our string after it's gone through this modification routine. It's probably trying to compare those eventually, right? And here's the compare, and it's doing a byte-by-byte comparison, which is what this line is. Repeat, a compare, byte, pointer, this address to this address, right? ESI to EDI, compared byte by byte. We'll hit F8 there, which it finished the compare. Oh, we jumped past success. We failed. So, that being said, does anybody figure out what the string is yet? Or at least how to get the string? Can anybody talk me through how to get that string? And we've looked at the entire algorithm that's used.
Decrease the value of the second string and the ASCII value by 1.
Right, and has anybody done it yet?
Slackers.
I heard somebody say it. Somebody say something back there?
How's it done? I couldn't hear it.
Yep. I'll tell you. Gotta get all my backwards. I'll go through it up here so you can see it. So this section, this is your section of code that we're essentially analyzing for the modification. And essentially what's happening right here, these two lines, which if you look at it, 401, 28E, and 89, is that it's actually taking our string, which is sitting here, and it's incrementing by 1 each character in that string. Okay? And then comparing it against this. So how do you do that in reverse? You take this string and you decrement it by 1. So going backwards, just because it's easier for me, it's going to be 1, 0, 0, capital B.
Dash.
Thank you. Dash. Right. Exactly. Dash, because that's getting modified, right? That's being checked earlier. Dash. R. Capital A. Okay, essentially you work it backwards. And I'm trying to remember what it is. Something like pulsar 001 with dashes every 3 characters is the answer. Okay? So one thing to note too, the loop actually goes 1 short. If you pay attention to the modification loop, it doesn't do the first character, which also tends to catch people. So it's pulsar 001. So let's see if that works. So we hit F9 to continue to run through. That starts it back up and lets it continue running. If it will continue running. There we go. So let's try it. Oh, I got to remember the caps off the top of my head too. P-U-L dash. Is this capped? Let's see. P-U-L. Oh, it's capital L. Dash. S. Yep, lowercase. Capital A. R. Dash 001. Check. All right. Now you could normally, what I would normally do is just let it run through and see if it pops, but we'll go through and we'll actually step through the loop and you'll see it hopefully end up coming out to a perfect match, which it does. There's your compare. Do a byte by byte compare. Jump if not equal. Go ahead and finish the run. Cracking success. We just walked through a very simple, straightforward crack. Does anyone have any questions? Yes, sir.
How many times did it go through that cycle? Just once?
Which cycle?
We changed all the values 1 time. Does that mean if I made all the characters 3 less instead of 1 less, it would cycle through that 3 times till it came up with the same thing?
If your code was specifically looped and designed, I mean, there's a couple different ways you could design it, right? You could write your code to loop through 3 times, each time changing it once. Then your code would look something like that with a second loop around it.
So you could have 3 possible codes then, depending on how many times it was allowed to loop?
Just depends on how you wrote it, right? So if you wrote your program, this little cracking thing, little test.
To loop up to 10 times.
You could loop as many times as you want. You could shift it by whatever.
So I could have 10 different key codes.
Sure, if you wrote it that way. Yeah, I mean, if you wrote the check to say if it matches this one, this one, this one, this one, this one. Yeah, absolutely. But right now, this thing's only set to, off by 1, essentially. It's a whatever, ROT 1 encryption, whatever you want to call it. Pure garbage, shift 1. So does anybody else have any questions on how that works? I mean, that's, like I said, very straightforward, basic crack of a program. Question? Comments? Tyler, go to hell.
Are you going to get into just dropping out comparison to slide right into the crack process?
he brings up the point, well, why don't you just nop out the compare? A nop is a no-op, and it essentially skips. And yes, that's cheating, but you certainly could have done it. It would have worked just fine. So essentially what you could have done to make this easier is essentially the line where you actually have, oops, and just restart it again so we still code. The line where you have,
You have to get past lag.
which you could knock out the check for that too.
Yeah.
You can knock out the compare there too. Message box, set window text, get window text, get window length. So here's the line. The line he's calling out right here for the first test. This is the compare. You could essentially throw a 0x90 opcode or a NOP, a do nothing code, for the compare and the jump, and it's just going to slide right through and continue through the operation. So you can actually go in with a hex editor, and I think you can do it in Ollie. I'm more used to using IDA, so I'm not sure.
Yeah, you do it.
I'm fairly certain you can do it in IDA, but anyway, in Ollie. But anyways, you essentially modify this code, fill with NOPs. Did that work? I'm not sure if it worked or not.
No, you have to, if the instruction is more than one thing, it'll fill the extras. So just
Zero.
like not, yeah.
Can I do 0x90? Do I have to do NOP?
I don't know what it'll do.
Well, let's just put a NOP in there. Oh, there we go. Bingo.
And it fills the rest up.
Yep. Okay. So remember how I talked a little bit earlier too about how operations require an opcode and your operands? What you see here is actually this particular opcode that was there took an opcode and two operands to operate, and it actually knocked out all of that. So it didn't just knock out a piece of the instruction, leaving the rest of the gobbledygook to screw up the code, and knocked out all three. And we'll actually do the same thing here. We'll knock that out. Okay. So that now we no longer have a check within the code for the length. And if you go down a little further, and which ones do we have to do here? We have to definitely do that. Actually, screw it. We'll let it compare and just knock the jump. Nop. Cancel. Restart. Now, let's see. Yeah, see, it didn't save it. I forget how to do that now. You actually have to push it into the binary because it changes it in volatile memory. And then when you restart it, it dumps out the old code, brings in the new one. So you actually have to push it into the binary. So you may have to do it with a hex editor, go into the binary and just edit those particular bytes within the code, which you can find by the offsets.
You can,
Yeah, I think if you right
you
click
can break before.
Yeah, just modified inline.
Yeah, you can modify it.
All right, so actually what he's saying there is modifying it inline. So we're broken right before the compare, I think, right?
The jump.
So, and actually, I talked a little bit about EIP, so you can see here, the next command to be executed is going to be 004012A0,
Knock that out.
which will be our compare. Actually, you don't even have to knock the compare, you just got to knock the jump. So we'll go ahead and run the compare. Now we'll knock it out here. Oops, what am I doing? And OP. And actually, just go ahead and knock this one out while we're here. And OP. And now we should just be able to let it run through. I started it up, and it didn't work. How cool is that? Register version. So where are we going wrong? Run. Check.
Maybe you
Can you just change the compare to say if it doesn't match this
or change
string?
or change the
Yeah, I mean, these are all perfectly valid ways of doing it.
change the
I'm just more of an IDA guy, so I'm struggling with the Ollie debug interface.
And that way only the real registration code would not register it.
Yeah, you could definitely do that. But again, I'm not sure how to do all this in Ollie, but it can certainly be done. I usually, if I get this far in Ollie, I usually end up dumping it into a hex editor and just editing it by hand. See there, it ran through the Opcodes. Let's go ahead and knock out these again. And continue. Runs through those knops. And so we definitely passed the first check there. Oh shit, I'm an idiot. I always go too fast. Get window text. Oh, so you got to knock out all of these compares as well, right? Because it's looking for the dashes.
You can modify the jump.
Yeah, just knock the jump there. Knock the jump there.
Sounds like a rap song.
Knock the jump.
Yeah, no.
Actually, before I go too far and screw it up again, I'm going to knock that one. Knock the jump here. Now that should have done it. There we go.
Yay.
So you had to knock out, what, 4 checks, 4 compares. That's cheating. Because you didn't actually reverse engineer anything, you just cracked it, which, as far as cracking is concerned, the end goal is cracking. Who cares about reverse engineering? But we're here to look at reverse engineering, which is why we wanted to walk through the full algorithm. So, any other questions on the first crack me? I have no idea how much time I have if we're going to be able to get through the second crack me. I have 6 minutes, so it doesn't sound like we're going to get time to get through any more, but I can definitely, if people want to walk through them, I'll walk through up to the first 3 out in the lobby, between other talkers or other speakers. I got no problem with that. And only the first 3 because I haven't done 4 or 5 in like 8 months, and I'm too lazy to try to sit there and figure it out with you. So, any questions? Yes, sir.
So this is going to be, this is pretty useless against a lot of modern authentication methods. Require you to phone home with whatever you put in, and then it compares that on their side.
Yes and no. At some point, a confirmation comes back to you.
Yeah.
Right?
Okay.
So get in there, RE the confirmation code, and when the confirmation comes back, modify it there. You could also reverse engineer the actual protocol that's being transferred back and set up a proxy and intercept the response. Like a lot of times it'll just be an HTTP post to a web server, and then the response comes back with the OK, go ahead. So you modify that. There's a number of ways. Cracking is just a great challenge. There's so many different ways you can attack these things, as you saw by the fact that he would have chosen to knock them out as opposed to bothering to reverse engineer all of the actual code. So there's just a number of different ways you can attack these things. Yes, sir.
How common? Is this like a first thing you check out to if you want to hack something? Or on a scale of 10, how often would you do this versus just waiting for somebody to publish a code problem?
Well, it depends on your goal, right? Cracking, a lot of guys out there want to be the guy that puts out the first key gen, right? So that, might be something to do with this. I don't crack. I just think cracking is a great way to learn reverse engineering. I use reverse engineering more for exploitation development and actually figuring out, okay, well, how is this program reacting to my overly long string? All right, let's drop it in the debugger. Let's see where my string comes into memory. Let's see what kind of compares it's doing. Oh, look, it's trying to copy that into a buffer that's too small. And now we can overwrite the stack, and we have a stack exploit. Stuff like that. So I use it more in exploit development than I do in actual cracking of software. But it's just, cracking is the easiest way to present it. Any other questions?
So you had mentioned briefly on the various ways that they'll pack these binaries and encrypt them.
Yes.
So since all of these are ran on an X86 system, there has to be some sort of baseline or entry point that it's going to use to get into these binaries.
Right.
Is there any method to the madness as to how to figure out what encryption algorithm they use, if it's an AES, triple DES, or MD5, whatever? Any tips there?
The thing to remember with packing is you're not going to have to decrypt it yourself, because the binary has to decrypt itself at some point to execute in memory. So what the hardest part about manually unpacking is finding what's called the OEP, or the original entry point to the application, because essentially what a packer does is it wraps that binary with its decryption code, encrypts the original payload, wraps itself, and then has decryption code that gets executed first. So it's getting through all that decryption crap until your original code is unencrypted, and then you have what's called the OEP, the original entry point. That's the hardest part. It really doesn't matter if it's encrypted with, super duper uber encryption 101. It doesn't matter because I don't care, because all I care about is seeing the unencrypted result. Anything else? Absolutely. They're the strongest encryptors. All right. I'll be around all day. I'm not going anywhere, so if you need anything, let me know.
Try the field.